In this chapter, we will discuss consolidation of clays, mainly saturated clays. When we construct a building or an embankment on top of a saturated clay layer, the clay is squeezed and some water drains out and the void ratio decreases. Due to the low permeability of the clay, this process occurs over a long time and is known as consolidation. As a result of the reduction in void ratio, settlement occurs over a long time in clays. Granular soils settle too, but they occur almost instantaneously. They have high permeability and are freely drained, and hence the consolidation process is almost instantaneous. Here, we apply a surcharge Q on top of a saturated clay layer, and see what happens to the total and effective vertical stresses, and the pore water pressures at a point X. Let's call the increases as delta sigma dash, and delta U. These increases are functions of time. Yes, they change with time. Here, we note the initial in situ values of the total and effective stresses, and the pore water pressure at X. The subscript O denotes overburden or initial in situ value. What you see in green are the changes in sigma dash, and U, which are caused by the applied surcharge Q. Consolidation is all about the changes. Let's not worry about the initial values. Initially, just after loading, the entire surcharge Q is carried by the water in the form of excess pore water pressure, delta U. With time, drainage takes place from the clay and the excess pore water pressure dissipates, transferring the surcharge load partly to the soil skeleton, thus increasing delta sigma dash. After very long time, the entire surcharge Q is carried by the soil skeleton, where delta sigma dash equals Q, and delta U equals 0. Here, you can see the variation of delta sigma dash, and delta U with time. At time of infinity, the consolidation settlement reaches an asymptotic value of SC, which is the final consolidation settlement. When that occurs, there are no excess pore water pressures, but we still have the in situ initial pore water pressures. During consolidation, at all times, delta sigma equals Q equals delta sigma dash plus delta U. All the discussions here assume one-dimensional consolidation. That means, the drainage of water and the strains are purely vertical, nothing laterally. In reality, this assumption is true when the surcharge Q applied at the ground level is spread over a very large extent. When the loaded area is small, the consolidation is not really one-dimensional, it can be two- or three-dimensional. Let's say the initial thickness and the void ratio of a clay layer be H0 and A0. At the end of consolidation, the thickness decreases by delta H and the void ratio decreases by delta E. The vertical strain of the clay is delta H on H0. Here, we are looking at the phase diagrams at the beginning and end of consolidation. The average vertical strain is delta E on 1 plus E0. Equating the two expressions from the previous two slides, delta H on H0 equals delta E on 1 plus E0. This is a very useful equation, we will use often in calculating the consolidation settlements. Coefficient of volume compressibility, denoted by MV, is a measure of the compressibility of the clay. Higher the value, more the clay compresses during consolidation. It is defined as the volumetric strain per unit increase in effective stress. In one-dimensional consolidation, volumetric strain is the same as delta H on H0. Here, V0 is the initial volume. Here, we show a scale for MV, starting from almost 0 for a very stiff clay to more than 1.5 MPa to the power of -1 for a very soft clay. The reciprocal of MV is known as the constrained modulus T. Constrained modulus is similar to Young's modulus, it is just that the clay is constrained from any lateral deformations. So, understandably, constrained modulus is generally larger than the Young's modulus. Only when the Poisson's ratio is 0, they are equal. Here, K and G are the bulk modulus and shear modulus, respectively. You will understand from this illustration why constrained modulus is larger than the Young's modulus. In both cases, we plot the stress against strain and look at the slope of the line. When the specimen is laterally restrained, it requires a larger stress for the same strain. In this example, we compute the final consolidation settlement from the definition of MV. Delta H is the same as SC, the final consolidation settlement. Let's discuss the one-dimensional consolidation test we carry out in the laboratory on an undisturbed clay specimen taken from the site. To ensure the drainage and the strains are both vertical, we contain the cylindrical disc-like clay specimen in a rigid metal ring. Typically, the specimen is 50 to 75 mm in diameter and 20 to 30 mm in thickness. A porous stone is placed at the top and bottom of the clay specimen to provide drainage during consolidation. The ring is submerged in water to ensure saturation during the test, and loaded in increment, and the settlement is measured with time, ideally over 24 hours for each load increment. The consolidation apparatus is also called odometer. In a consolidation test, the applied pressure on the specimen is generally doubled every day, allowing for complete consolidation between the increments. The settlement and hence the void ratio at the end of consolidation are determined for every applied pressure. After reaching applied pressure of about 1000 kilopascals or more, The specimen is unloaded in 3 or 4 steps, computing the void ratios at every step. Understandably, the specimen heaves and the void ratio increases during unloading. Here, you can see some undisturbed Shelby tube samples of clay, where the ends are waxed and wrapped in plastic sheets to maintain the moisture content. There will be few days between the sampling at the site and the laboratory testing, and it is necessary that we preserve the samples carefully. You can also see the 75 mm diameter odometer ring, a porous stone, and the top cap for loading. Here you see 2 different consolidation test setups. The photograph on the left shows 3 front-loading odometers, where the load is applied on a hanging arm using dead weights and leveraged. The right one is a servo-controlled setup with pneumatic loading, where compressed air is used to apply the vertical load. From the data generated from a consolidation test, the void ratio is plotted against the effective applied vertical stress sigma V' on a log scale as shown. The loading path is shown in orange and the unloading path in green. This plot is called the E log sigma V' plot. The E log sigma V' plot generally consists of straight line segments of 2 very different slopes. The slope of the latter part of the plot is called the compression index, denoted by Cc. The slope of the unloading path is called the swelling index Cs or recompression index Cr. If the clay is reloaded after unloading, it follows the same path as unloading. The loading path, shown in orange, takes a sharp turn at the pressure of sigma P', changing the slope from Cr to Cc. This value of sigma P' is known as the pre-consolidation pressure, similar to the yield stress of a material. You will realize soon that this is the maximum pressure the clay has experienced ever in its history, which could be hundreds of years. In this exercise, we will do a complete set of calculations from a consolidation test. We will do parts B and D a little later, after we understand a few more terms. Here, we have the E log sigma V' plot, which clearly defines the loading and unloading paths. We can see that the pre-consolidation pressure is around 30 kilopascals, where we see a sharp turn with a significant increase in the slope. As usual, MV varies with the effective stress. Usually, in settlement computations, we select a value appropriate to the stress level. Let's say E0 and sigma V0- are the initial or in situ values for a clay. When the clay is loaded, it moves along the green line and reaches the pre-consolidation pressure sigma P-. From here, it takes a sharp turn on further loading and compresses with a slope of cc. The blue straight line you see, with a slope of cc and coinciding with the loading path, is the virgin consolidation line. It is a unique line in the E versus sigma V- space that is specific to the clay. As soon as the loading path hits the virgin consolidation line, the clay reaches its pre-consolidation pressure, and follows the virgin consolidation line, or VCL, while compressing further. Over-consolidation ratio or OCR is the ratio of the pre-consolidation pressure to the effective vertical overburden stress. The OCR must be greater or equal to 1. You can see from the figure that further the in situ values are from the VCL, larger is the OCR. If the in situ values plot on the VCL, the clay is called normally consolidated. If they plot to the left of the VCL, they are called over-consolidated. Close to the VCL, the clay is slightly over-consolidated, and far from VCL, it is heavily over-consolidated. Here, we are looking at E versus log sigma V- plots, both in the laboratory and field. Both have the same VCL shown in green. The clay is initially over-consolidated. With loading, it reaches the pre-consolidation pressure and follows the VCL. This relationship can be proven theoretically. This applies during consolidation due to any stress increment. For over-consolidated clays, Cc has to be replaced by Cr. Cc, Cr, and Mv are all measures of the compressibility of a clay, which is opposite to stiffness or Young's modulus. There are more than 50 empirical equations, relating compression index with natural moisture content, initial void ratio and liquid limit. Some of these correlations are regional, which are developed for clays from specific regions. Some are more general and apply to all clays. Recompression index is generally 1/10 to 1/5 of the compression index. Modified compression index, also called compression ratio, is simply Cc on 1 plus E0. Similarly, modified recompression index or recompression ratio is Cr on 1 plus E0. Some practicing engineers prefer using these modified indices to eliminate the effect of E0 in the settlement calculations we will discuss shortly. These modified values vary in a very narrow range. For example, modified compression index varies in the range of 0.2 to 0.4. Here are some thoughts on E versus log sigma V dash plots. What you see on left is the reality and right is idealized. When the clay is unloaded and reloaded, which can be more than once, there is some hysteresis. The unloading and reloading paths are not really the same. We approximate them as the same. When a reloading path meets the VCL, it simply follows the VCL until next unloading takes place. From the last slide, we saw that the unloading and reloading paths are the same, with a slope of CR which is the same as CS. The 3 points A, B, and C are at different E0 and sigma V0 dash values. When the clay layer is loaded at the ground level, the loading paths coincide after they reach their respective pre-consolidation pressures. The clay is initially at A, where the pre-consolidation pressure is sigma P1-. While loading, it exceeds this value and follows the VCL. When it is unloaded at B, the clay becomes over-consolidated again, with the new pre-consolidation pressure sigma P2-. Therefore, note that the pre-consolidation pressure is not permanent, this can change. The point A defines the in situ values of the void ratio and effective stress. With the VCL fixed in the space, the pre-consolidation pressure is fixed too. In its geologic history, the clay must have followed VCL and unloaded to reach the current state. This may have happened hundreds of years ago. The clay still remembers that. The consolidation settlement can be computed using MV or the E log sigma V- plot. The problem with MV is that it is stress dependent and hence we have to select the value right. The second method using the E log sigma V- plot is better. Here, we determine the consolidation settlement SC as delta E on 1 plus E0 times H0. E0 can be determined from the moisture content and the clay is saturated. H0 is known from the bore logs. How do we find delta E, the reduction in void ratio during consolidation? Let's look at 3 different scenarios for computing delta E. In the first, the clay is normally consolidated and hence moves along the VCL during consolidation. the effective stress increases by delta sigma dash and hence the delta E can be computed as Cc times the change in log of the effective stresses. In scenario 2, we are considering an over-consolidated clay, which remains over-consolidated at the end of consolidation. That is, the clay has not hit the VCL yet and hence sigma VO dash plus delta sigma dash is less than sigma P dash. Here, the equation for delta E is almost the same as the previous one, but we replace Cc by Cr. The scenario 3 is also for over-consolidated clay, but during consolidation, it becomes normally consolidated. Due to the loading, pre-consolidation pressure is exceeded. Here, the loading path consists of two straight line segments and the void ratio changes have to be added. Preloading or surcharging a normally consolidated clay layer is a common technique to make the clay over-consolidated and hence settle less once the structure is built. The preload is maintained for 6 to 12 months to ensure the clay is almost consolidated and then removed. The preloading and the removal of the surcharge are shown as paths A, B and BC, respectively in the figure. Sampling tubes are used to recover clay samples from the sites at various depths. The samples undergo mechanical disturbance due to the sampling operation, and also stress relief due to the removal of overburden pressure. The disturbance is mostly pronounced along the annular region of the sample near the wall. The inner core is relatively undisturbed. Sample disturbance can destroy the clay fabric and lead to underestimation of the strength and stiffness. Due to sample disturbance, the E versus log sigma V dash plot from the lab may look like this, with no well-defined pre-consolidation pressure. How do we determine the pre-consolidation pressure from this? What we want to do here is to convert the laboratory curve to what we expect from the field if there was no disturbance. Let's do this in two parts. First is to determine the pre-consolidation pressure and then to define the virgin consolidation line and the field E versus log sigma V dash plot. There are a few different ways of determining the pre-consolidation pressure from the lab curve. Of these, Casagrande's method is the oldest and most widely used. There are suggestions that Casagrande's method is influenced by the scales selected for the x and y axes. Pacheco Silva's method and Oikawa's method appear to give better definitions of the pre-consolidation pressures. Oikawa suggested that having log of 1 plus E on the y-axis gives two straight lines, the intersection of which is the pre-consolidation pressure. Schmartman in 1955 observed that no matter how much the disturbance is, all E versus log sigma V dash plots for the same clay will converge at the void ratio of 0.42 E0. Here are the procedures for establishing the VCL and the field curve for normally and over-consolidated clays. Note that, in over-consolidated clays, the lab curve must include an unload-reload cycle to define the recompression index. So far, we have looked at methods to determine the final consolidation settlement SC, which occurs after an infinitely long period when the excess pore water pressures have fully dissipated. In the next few slides, we will see how we can determine settlements and excess pore water pressures at a specific time. When a surcharge Q of large lateral extent is applied at the ground level, excess pore water pressure delta U naught equals Q is developed at all depths within the clay. With free draining boundaries at the top and bottom, there is instantaneous dissipation at the two boundaries at all times. The excess pore water pressures start dissipating with time, with drainage occurring through the two boundaries. At time t, the variations of the remaining excess pore water pressure and the dissipated excess pore water pressure with depth are shown here. At all times, and at all depths, the constant initial excess pore water pressure, delta U naught, is shared between the dissipated and undissipated excess pore water pressures. The undissipated excess pore water pressure delta U, and the dissipated excess pore water pressure delta sigma dash, within the clay vary with depth and time. Remember sigma equals sigma dash plus U. Looking at the changes, delta sigma equals delta sigma dash plus delta U. At all times, and at all depths, the constant initial excess pore water pressure delta U naught is shared between the dissipated and undissipated excess pore water pressures. These are the assumptions made by Terzaghi in 1925, in coming up with his famous one-dimensional consolidation theory. Here, we are looking at a point, shown as an infinitesimal element. From mass balance, we have an expression at the bottom of the slide for the net volume of water squeezed out of the element per unit time. From the definition of MV, we develop an expression for the volume change per unit time, which is the same as the water squeezed out per unit time. Let's equate the two expressions from the last two slides, and that gives the governing partial differential equation. Here, CV is the coefficient of consolidation, defined as K on MV on gamma W. Note that the U we have in the partial differential equation is actually delta U. The consolidation theory deals with the excess pore pressure delta U. The unit of CV is length squared per time. It is commonly expressed in millimeter squared per minute, centimeter squared per second, or meter squared per year. Here are the boundary conditions to solve the governing partial differential equation. We can show that the excess pore water pressure at a point is a function of the initial excess pore water pressure, depth of the point, time considered, coefficient of consolidation and the average maximum length of drainage path HDR, which is explained in the next slide. Here, we are looking at two scenarios, doubly drained and singly drained clay layers of thickness H. The drainage layer at the top or bottom can be any free-draining granular soil. From a point within the clay, the drainage path can be upward or downward, depending on which is the shortest. In a doubly drained layer, the maximum length of drainage path would be half the thickness. We will use the average length during the consolidation process where H decreases with time. Here, we have the final solution for delta U on delta U naught as a function of depth factor, big Z, and time factor, big T. These two factors are dimensionless. We simply express time t as a dimensionless time factor t, and depth c as a dimensionless depth factor. The degree of consolidation varies with time and depth. At time t and depth z, it can be defined as the ratio of the dissipated excess pore water pressure to the initial excess pore water pressure, and we will use a symbol uppercase U. We have an expression here for U as a function of big Z and big T. Here is a simple example where we have used the expression from the last slide to compute U for a given Z and T. It takes quite a bit of time, and hence we developed a graphical solution. Here is the graphical solution, which applies to both singly drained and doubly drained clay layers. You can see that the degree of consolidation is the minimum when Z equals 1. At Z equals 0 or 2, the degree of consolidation is 100% at all times, which is one of our boundary conditions. The plots are symmetrical about the horizontal axis at Z equals 1. While the degree of consolidation U at a time varies with depth, we like to have an overall average degree of consolidation for the layer. We define this as the area of the dissipated excess pore water pressure versus depth diagram over the area of the initial excess pore water pressure versus depth diagram. Have a good look at the figure here. Here is the equation for the average degree of consolidation, which is a function only of the time factor, big T. Here is an example of computing the U average for a specific time factor. Again, quite a bit of work. Here is the graphical representation of the average degree of consolidation as a function of time factor. Two sets of values worth remembering are, for U average equals 50%, D equals 0.197, and for U average equals 90%, D equals 0.848. Here, we have two sets of equations relating U average, and T1 is for U average less than 60% and the other is for U average from 60% to 100%. Casagrandes and Taylors are two standard methods used for determining the coefficient of consolidation CV from the laboratory consolidation test data. There is also Asaoka's method, quite popular among practicing engineers, especially when field settlement observations are available. In Casagrandes' log time method, time is presented in x-axis in logarithmic scale. The graphical procedures for determining D0 and D100 are shown in the figure. From the two, D50 is determined, which defines T50. Noting that the time factor for 50% average degree of consolidation is 0.197, CV can be determined. In Taylor's method, square root of time is shown on the x-axis. The linear portion of the plot is extended backwards to meet the y-axis, defining D0. The point corresponding to 90% average consolidation is identified as shown in the figure. From T90, CV is determined. Asaoka's method requires settlement records over a certain period, taken at equal time intervals delta t. The settlements are plotted against each other. The second reading on the y-axis is plotted against the first reading on the x-axis. The third reading on the y-axis is plotted against the second reading on the x-axis. Continue this for all the readings and draw the line of best fit. The intersection of the line of best fit and the line of equality define the end of consolidation. What we call here as S sub EOP is the same as the final consolidation settlement SC. EOP stands for end of primary. CV can be determined from either of the two expressions given here. Terzaghi's one-dimensional consolidation theory suggests that the consolidation process goes on forever and that the final consolidation settlement is reached only at time of infinity. In reality, consolidation process ends after some time, which could still be long. As shown in the figure here, consolidation finishes at time Tp. Here, P stands for primary consolidation. At this time, the excess port water pressure has fully dissipated. Beyond this time Tp, the clay continues to compress due to realignment of the clay particles in a process called secondary compression or creep. During secondary compression, void ratio varies linearly with log of time. The slope of this line shown here is known as the coefficient of secondary compression, C alpha. C alpha on CC ratios are typically constants as given in the table. As a rough estimate, this can be taken as 0.05 for normally consolidated clays. For over-consolidated clays, C alpha can be significantly less, possibly by an order of magnitude. Here is the expression for the secondary compression settlement occurring up to time t since the completion of consolidation.